In this video, we're going to talk about density. Density is mass over volume. In other words, density is the amount of mass per unit of volume. You can think of it as a measure of how tightly packed an object is. For example, if you think of a crowded room, a room with a lot of people, you would say has a high density, more dense is more dense than a room that has less people. That would be considered less dense. So it's a measure of how tightly packed an object is. So if we take a look at example one, and you might want to pause the video, read through it, and then unpause once you've read the question and have thought about it. But we have an aquarium manager that's drawing a blueprint for a fish tank. And in the center of the fish tank is a hole. And that's where people can actually stand and look at the fish that are swimming around. They're telling us in the question the best average density for the fish that will go in the tank is 16 fish per 100 gallons of water. And since density is a measure of how tightly packed an object is, this amount of fish, 16 fish per every 100 gallons of water, will make sure that there's enough room for the fish to swim around while making sure that people can still see fish and there's not areas of the fish tank where there's no fish where in front of people. The aquarium right now has 275 fish available, and they want to know whether they have too many fish and they need to not put all of them in the fish tank, or if they have too few fish and they need to go out and get some more fish in order to achieve the amount of fish that would be the good amount for the tank that they have. So that's our goal, to determine if they need more fish or if they have too many fish. So that way they know. So in order to figure that out, first of all, we're going to have to find out how much space is in this tank to begin with. So when we're talking about how much space is inside something, we're talking about the volume. So in order to find the volume, we're going to have to find the volume of the whole fish tank. And we're going to have to find the volume of the hole in the center. And then once we have the two volumes, we can subtract in order to find what can go in the place where the fish go. So how much stuff, how much water can go in where the fish go, because that's the part that we're interested in, the part that can actually hold the fish. So to find the volume of the tank, we are going to have to use the volume of a cylinder formula. We can find the volume of a cylinder using the formula volume equals pi r squared height. So I'm going to put that down over here. Volume equals capital V times H. Since the area of the base is a circle, it is pi r squared height. And it's the same thing over here for the hole, because the hole is also cylindrical shaped as well. So now we have to figure out what the radius is that we're plugging in. So the whole tank is from the outer to the inner, right? That's halfway across the entire tank. So it's the 3 feet plus, this is 2 feet, so this is also 2 feet, because the radius on the bottom base has to be the same as the radius on the top base, because it's the same cylinder that we're looking at. So in total, that is a radius of 5 feet. And the fish tank has a height of 4 feet. For the hole, the radius of the hole is 2 feet. And the height is once again 4 feet. Everything is in feet. So here we have 100 pi cubic feet. And here we have 16 pi cubic feet. And then if we subtract the two, we get 84 pi cubic feet. And that's the volume of the hole. That's the volume of the part where the fish go and the water go. So that's the amount of water that can go inside of this fish tank. So now we have to figure out, for this amount of space, if there are too many fish or too few fish. So in order to do that, I'm going to have to use the desired density, the best average density that they provided to me in the question. 16 fish per 100 gallons of water. In density, the first unit is the mass unit. So the mass, the object that we're talking about, is the fish. That's what's weighing on the tank here. It's the fish. And the second unit is the volume unit. So 100 gallons is the volume here. But wait, our volume was in cubic feet, not in gallons. So in order to use this density, I'm going to have to use the conversion that they provide, that for every cubic foot, there are 7.48 gallons. So what I'm going to do is I'm going to take my volume in cubic feet, and to convert it to gallons, I'm going to multiply by 7.48. And I'm going to do that on the calculator so that you can see. 84 pi times 7.48. And I'm going to leave a couple decimal places until my very last step. So 1973.925. And that's how many gallons of water can fit in the fish tank. And now I'm all set to use density, the density that they provide. So density equals mass over volume. So the density is 16 fish per 100 gallons of water. Notice right here, fish per 100 gallons of water. So density is equal to mass. That's what we're trying to find. We're trying to find the number of fish that would be the good amount for this tank. And then the volume, we found it before. It would be this number over here in gallons. And now we can cross multiply and we can figure it out. So I have 100 m equals to that really long number times 16. Let's do it. 31582.808. And then we're going to divide by 100. And we get 315.8 fish. But you can't have 0.8 of a fish. So if we round up, well, that's more fish than can fit because only 315.8 fish can fit. So if we round up to 316, the fish might be overcrowded in the tank, or the tank might break because we're exceeding the capacity. So we're going to have to round down to 315. So the aquarium has 275 fish available. So I think it's clear they have to get more because the tank can actually hold comfortably 315 fish. So let's figure out how many more they have to buy or get or fish out of the ocean. 315 minus the 275 that they already have, and that is 40. They must add 40 fish. And there we go. Moving along to the next question. You might want to pause the video and read it and then unpause. This is a question on population density. And population density just means that we're dealing with density of living creatures. So it's actually exactly what we did in the previous example, because even though we were using D equals M over V, we were talking about living things. We were talking about the fish. So here it's talking about the population in different counties of New York State and the area that the people occupied. So our density formula is D equals M over V. When we're talking about living things, so population density, the mass refers to the number of living things. Just like in the previous example, that referred to the number of fish. That was our mass. Divided by Our volume we can think of as the space the living things occupy. So, for example, in our previous example, the space that the fish occupied was the tank that they could be in. So, the gallons of water that could fit in the tank was our volume. So, just something to keep in mind. We're trying to figure out which county had the greatest population density. So, all we have to do is the number of living things, in this case people, divided by the space that they occupy. In this case, the area that they are inhabiting. So the population would be the mass, would be the number of people, and the land area would be the volume, the space that they're occupying, the amount of land that they're on. So for each one, all I have to do is divide M over V to see what the density is and see which one had the greatest. So I'm going to do Broome first. 200,536 divided by, I can't remember these numbers, 706.82. And that's the population density, 21636.8. Just going to make a note of that. Just going to write Broome I can't remember, 21636.8. Okay, now Dutchess, 280,150 divided by 801.59. And that's smaller, much smaller actually, 349.5. And then we have 219,846 divided by 522.95. Okay, bigger, but still a lot smaller than the first one, 420.4. And then the last one, 200,635 divided by 811.84. And that's 247.1. My first one seems pretty off, so I'm going to do my first one again. It's very far off from the other numbers. So 200,536 divided by 706.82. Oops. Keep doing that. I'll get it right this time. Okay, 283.8. I must have typed in a digit wrong before. Okay, so the greatest population density is Niagara. Moving along, you might want to pause the video and take a look and read the question, and then you can unpause in order to see how to do the question. So what we're trying to figure out here is we're trying to figure out the weight of the entire training equipment here, not just the filled base on the bottom that's going to be filled up with, what's it filled up? What's it being filled up with? Sand. So not just the bottom base that's being filled up with sand, but also the unfilled base, because the unfilled base, so that's what it is before the sand is added. So we need to take that into account as well. So at the end, we're going to make sure that we add on the 270 pounds to get the total weight of the bag, the pole, and that unfilled base, the entire training equipment. So the first thing I have to do is I have to find the volume of the part of the equipment that's being filled up with sand. And it says in the question that the cylindrical base is what's being filled up with sand. And it's 18 inches tall, so that's the height. And there's a diameter of 20 inches, so I can get the radius. The radius would be half of that, which would be 10. I also see there's another number here. The base weighs 95.46 pounds per cubic foot. Since there's 2 units attached to this number, it is the density. It has the mass unit and the volume unit. But check it out. The volume unit is in cubic feet, but our dimensions for the base, the height and the diameter, were given in inches. So what I'm going to do before I get started is I'm actually going to convert the 18 and the 20 inches into feet. And I'm going to do that by dividing by 12. So I'm going to take the 18 inches and divide by 12 in order to get feet. And I'm actually not going to divide 20. For the volume formula, we need the radius. So the radius would be 10, half of 20. So I'm going to take 10 inches and divide that by 12 in order to get in feet. So I'm going to use my calculator. And if I use the fraction button, it'll just put it into a fraction in lowest terms for me. So 1.5, or it'll give me a decimal. I can always convert it back to a fraction, but it's okay. It has an end. And then 10 over 12. And, oh, I don't like that. I'm going to change that into a fraction. 5 over 6 is the fraction in lowest terms. So what I'm going to do now is I'm going to plug into the volume of a cylinder, which is pi r squared height. So the radius we found is 5 over 6 feet. And the height is 1.5. So I'm going to type these numbers into my calculator, and that should give me the volume in cubic feet, which is what we need here in order to use the density. So pi 5 over 6 squared, and then that was 1.5. I gotta retype this. So pi 5 over 6 squared times the height of 1.5. And that's about 3.725. 3.2725. Okay, so that's the volume of the entire base of the training equipment, but it says that we're determining the weight of the training equipment if the base is filled to 85% of its capacity. So not if it's filled up all the way, this is all the way. We need 85% of its capacity. So what I actually have to do to find 85% of its capacity is I'm going to take our volume and I'm going to multiply by 85%. In order to multiply by a percent, you do have to change it into a decimal by dividing it by 100. So 85 divided by 100 is 0.85. So I'm going to multiply by 0.85 in order to get the 85% capacity. And that's 2.7816. And notice how I'm clearly labeling that this is still the volume, so that way I can understand what I'm doing here. So that's the volume to 85% of the total capacity. Now, since I have the volume to 85% of the total capacity, it's time for me to figure out the weight. And in order to do that, I need to find the mass, so I need to be using the density formula and the density that they provide to me in the question. So density is m over v. The density provided is 95.46 pounds per cubic foot. And we're looking for the mass, and the volume to 85% of the capacity we just found is 2.7816 cubic feet. And look, our volume units are both cubic feet, and they're canceling out, so that's great. And that means when we cross multiply, we're going to have our answer in pounds which is what we want. I'm going to put this over 1 and cross multiply. So we have m is equal to, and then I just have to cross multiply this way over here. Let me make sure that I do that. Times 95.46. And I get 265.5333. So that is the weight of the filled base. But we also have to account for the fact that it weighed 270 pounds when it was unfilled. So I do have to add that back now. And I'm going to make sure I round according to the question. I think it said to round to the nearest pound. So that would be 536 pounds approximately. Moving on to the next one. Please make sure that you pause the video and think about the question for yourself, and then you can definitely unpause the video. So we have a rectangular prism. I can't draw that, so I'm going to draw a flat rectangle. Sorry about that. And it has the dimensions 2 feet, 1 feet, and 18 inches. I hope that you realized that 2 of the dimensions are in feet and 1 of them are in inches. So we're going to have to convert either all to feet or all to inches. If you read the questions, you'll notice that in the second question, actually I messed this up here because this starts the second question here. But in the second question, it says the weight of a baseball is approximately 0.025 pounds per cubic inch. And notice how it uses cubic inches for the volume measurement in the density. This has 2 units, so it's the density. This 0.025 is the density. So the first unit that you see, the pounds, that's the mass unit for weight. And the second unit that you see, the cubic inches, that is the volume unit. So notice how the density is ultimately going to be using cubic feet. So it makes sense to change everything into feet. So in order to convert the 18 inches into feet, I'm going to just divide by 12. And that's 1.5. We did that in the last problem. So that's 1.5 inches. So you might be tempted to just multiply the dimensions together. Oh, sorry, 1.5 feet. We converted it from inches to feet. You might be tempted to just multiply everything together, length times width times height, find the volume of the sphere and divide. If you do that, if you tried that, you'll get an unrealistic number. You'll see that it doesn't make sense. It'll be way too few balls, and it'll seem like a small amount of baseballs for a box of this size. It's a pretty large box. It could probably fit more baseballs. I think you get 13 doing it that way. So you definitely don't just want to take the volumes and divide. And the reason for that is because we don't really care about the volume of the sphere right now, because we don't care how much stuff is inside the sphere. What we care about is how many spheres, how many baseballs we can stack in all of the directions to fill up the box. So basically, lengthwise, we want to see how many baseballs we can fit. And notice the line I'm drawing is through the entire ball. It's the diameter. So it's going to depend on the diameters. Same thing if we measure height or width. How many we can stack widthwise or heightwise is going to depend on the diameters of the ball. Because if we get to the end over here and we're trying to put another ball, let's say there's a little bit of space, well, it's not going to fit a full diameter of another ball, so we can't put it. So it's going to be the diameters that impact. So what we actually should do before we find the volume is we should take into account that lengthwise, widthwise, and heightwise, we can only fit based on the diameters. That's going to determine how many balls can fit. So I'm actually going to take the length, the width, and the height and divide by 2.94 to determine how many diameters can fit there, how many balls can fit there, because it's based on the diameters. So I'm going to do 2 divided by 2.94. I'm going to do 1 divided by 2.94. Oh. Backtrack a little bit, guys. Cubic inches is the volume. Cubic inches, not cubic feet. I totally misread that. So we should actually convert to inches. I'm going to do that first because it's going to be a lot easier. So 12 times 2, that's 24 inches. 12 times 1, that's 12 inches. Everything's in inches now. So just like we were doing, I'm going to take the length and divide by the diameter. I'm going to take the width and divide by the diameter. And I'm going to take the height and I'm going to divide it by the diameter. And I'm going to see what we get. So I'm going to do first 24 divided by 2.94. And notice how we get 8.1. We can't put 0.1 of a ball. And if we do 9 balls, that's not going to fit because it can only fit 8.1 diameter. So we're going to have to round down to 8. And then we have 12 over 2.94. Using the same reason, that rounds to 4. And then we have 18 over 2.94. Using the same reasoning, that rounds down to 6. So now if we use the volume formula for a rectangular prism, and we do 8 times 4 times 6, we get 192. And since this was how many diameters can fit in the box, this is how many baseballs, because it's how many baseballs can be stacked in all of the directions in the box. Moving on to the next part, we already determined that we have the density. And what it says is determine and state to the nearest pound the total weight of all the baseballs in the fully packed box. So it's giving us the density, and it tells us the weight of a baseball is approximately 0.025 pounds per cubic inch. So the density is for the baseballs. So we're going to have to, when we're using the density formula, we're going to have to use the volume for the baseball. So we're going to have to find that. So volume of a sphere, which is what a baseball is 4/3 pi r cubed. And since the diameter is 2.94, let me divide that in half to get the radius. And that's 1.47. And this is going to be in inches, cubic inches. $13.306. Okay, so the density is 0.025 pounds per cubic inch. We're finding the weight, the mass, and now we found that the volume is 13.306 cubic inches. If I put this over 1 and I cross multiply, m equals 2. Let me multiply by 0.025. And that's 0.3327. Wait, did I round that correctly? 26. So that's really low because that represents the weight of one ball. Not the full pound. Kind of makes sense, right? Because we found the volume for one sphere. So this mass represents the weight of one ball. We need for the fully packed box, and in part 1, we determined that a fully packed box has 192 baseballs. So all I have to do is take this value and multiply it by 192. And then I see that is approximately, it says to the nearest pound. So that is approximately 64 pounds that the baseballs weigh. So I'm going to write that here. That is approximately 64 pounds. I'll write here times 192, and that's approximately 64 pounds. Moving on to the next one, you might want to pause the video and think about it for yourself. But what we're trying to do here in the first part is we're trying to find the volume of the water tower. That's the first part of the question. So what we need to do is we need to find the volumes of the 3 parts and add it up. Let's start with the cone. So volume of the cone, that's the top part, is 1/3 pi r squared height. So I need the radius and I need the height. So this radius of the hemisphere is 8.5, and all radii of the same shape are congruent. So the radius of the circular part of the cone also is 8.5. So the radius is 8.5. We don't have the height, but we do have a side and an angle. So we could use trig because we do have a right triangle. So if I label from the 47-degree angle, we're finding opposite and we have adjacent. So if I write down SOHCAHTOA, opposite and adjacent is tangent. So tangent of the 47-degree angle is equal to, I'll just use h for height, the opposite over adjacent, which is 8.5. Cross multiplying, we have 8.5 tangent of 47 equals to the height. Now I'm going to plug in. So the volume of the cone equals to, sorry, my pen's being weird, 1/3 pi, 8.5 squared, and then the height is 8.5 tangent of 47. Now I'm going to find the volume of the cylinder. And that's pi r squared height because it's capital B times h. This one was 1/3 capital B times h. But for both of them, the cone and the cylinder, the capital B is the area of a circle, which is pi r squared. So that's where I got the pi r squared height and before the 1/3 pi r squared height. So for the cylinder, the radius is 8.5. And it gives us that the height of the cylinder is 25. And then finally for the hemisphere, we can find the volume of the sphere. And then we can divide it by 2. So that would be 4/3 pi. The radius is 8.5 cubed. And then we're going to divide that by 2. So I have a lot of typing into my calculator because now that I have all the volumes, all I need to do is add them together. But that's going to be a lot of typing into the calculator that I'm going to have to look back and forth for. So I'm going to get started. So 1/3 pi 8.5 squared (8.5 tangent 47). So that's for the cone. Now the cylinder, pi 8.5 squared 25. That's for the cone. And then we need for the sphere 4/3 actually I'll do it this way, 4/3 pi, and then the radius is 8.5 cubed. And then what I get from that, I need to divide by 2 because it's a hemisphere. So to that, I'm adding the volume of the cylinder. And to that, I'm adding the volume of the cone. And that's what I get. It says to round to the nearest cubic foot. So the nearest whole number, about 7,650 feet. Now for the second part of the question, it says that the water tower was only constructed to hold a max of 400,000 pounds of water. And it tells us that if water weighs 62.4 pounds per cubic foot, so 2 units, that tells us that this number is the density, and this is the mass, and this is the volume unit. So the mass is in pounds, and the volume's in cubic feet. And we already have our volume in cubic feet, so that's good to go. So if water weighs 62.4 pounds per cubic foot, can the water tower be filled to 85% of its volume and not exceed the weight limit. So first I have to think about what 85% of the volume is. So I got to take the volume that I found and find what 85% of that is. They like 85%. That was in one of the other questions too. So times 0.85, and that's 6502.8173. What was that? 6502.8174. Okay, and now I'm all set to plug into my density formula. We're finding the weight, so we're finding the mass. The density is 62.4 pounds per cubic feet. We're looking for the mass, and we just found that the volume to 85% of its capacity in cubic feet, so we just found that. So all good to go. Our cubic feet are going to cancel out, and that means our mass is going to be left in pounds, which is what we want. Going to put this over 1 and cross multiply. M equals, gotta times that number by 62.4. So I'm going to do that in my calculator. Times 62.4. Okay. And that's approximately 405,000. I'll just say approximately 406,000. So no matter which way you round it, it's going to be over the maximum of 400,000. So no, it will exceed the weight limit if you fill up this water tower to 85% of its total capacity. They got to fill it up less. Okay, you might want to pause the video and check this one out. So during an experiment, the same type of bacteria is grown into petri dishes, and it gives us the diameter of both of the petri dishes and how many bacteria are there after an hour. And what we need to do is figure out which petri dish had the greater population density. So D equals M over V. And remember, when we're talking about population density, what we're really just talking about is the density of living things, how spread out living things are in the area that they are inhabiting. So instead of mass, we're talking about the number of living things, but that is the mass. And then instead of volume, because that's for like inanimate objects, we're talking about the space the living things inhabit or occupy. So basically it's a measure of how spread out things are over a certain area. So how spread out the living things are over a certain amount of space. So here, how spread out the bacteria are in their petri dish. So in order to do that, I need to take the number of living things after an hour. So for both of them, this one is 40,000. That's the mass. And this one's 72,000. That's the mass. That's the number of bacteria after an hour. And then I need the space that the living things occupy. So since the petri dishes are both circular, I can find the space that they occupy by doing pi r squared. There is no height here for me to account for. The radius, 51 divided by 2 and 75 divided by 2, because they give us the diameters. So the radii are 25.5. And 37.5. So the pi r squared here would be pi 25.5 squared. And here it would be pi 37.5 squared. So let's start with petri dish A when we do density equals to mass over volume. So density equals to 40,000 divided by pi 25.5 squared. I'm going to do that in the calculator. 40,000 divided by pi 25.5 squared, 19.58. And that's the density, the population density. And for petri dish B, that's 72,000. The bacteria after the hour divided by the space they occupy, pi 37.5 squared. What was that radius again? 37.5. And that's 16.3 approximately. So A, Petri dish A has the greater population density at the end of the first hour. Oh, and that's all the questions for this video. We are done for this video. This was a long one.